So we can start in 1 minute. 1 minute. So we are continuing the session. So sir, you can proceed now.
Thank you, Sudhanshu.
Yes.
Okay, good evening again. So we are talking about flow that is that was happening in a straight line. So when you have the flow without any external disturbance, and that too if it is happening in a transitionally rough bed, then we can predict what will be the velocity of the particle that is moving over the transitionally rough rigid bed can be found out by the formula which you can see on the screen. Now what we did was, as I told, we tried to introduce an external turbulence, right? In a flow that is happening there, I just tried to introduce an external turbulence there. So for that, what we did was, we had an external setup like this. It was in the same flume, right? That in the same flume, in the working section where the sediments were captured. It was close to 12 meters downstream. So in that same working section, what we did was, it was previously without any disturbance. In between the middle of that, we have placed the circular, we have placed a cylinder there, right? And that was placed exactly in the middle of the flume, and you could see that we have placed it was a model of bridge pier, right? And yeah, cylinder was placed there, and because of this the flow gets disturbed and it gets deviated and it flows, and there's a lot of turbulence that will happen around this circular cylinder, right? And Sumir has made an interesting study where he tried to understand the external turbulence, and what he studied was like this idea we got from that only, right? What he tried to do was, it was an external flow that was there, and he also had an external turbulence. It was created. It was not a pier that was inserted there. It was an external turbulence he gave it from outside, and because of the turbulence that was generated, how the sediment behaves. That was a very interesting study he made. And in that, he tried to understand that if you did not consider, and what he concluded was, if you did not consider this turbulence into account, you will make a wrong prediction in bed load time. That's what he said. The transport increases remarkably with the increase in the turbulence level. So that understanding, that point was should be carefully understood, so that we will, whatever model simulations which we make, so we will take into account of this turbulence also, which was not previously done long back, right? So here, this external turbulence, what we did was, we had a setup like this, just to have. Do you have the video? Just to have how it happens, just I'll play this video. Will it run? Let's wait, and if it runs, okay, good. And can you see that? Can you see that the particle is moving? I don't
Yes,
know.
yes,
Uh,
sir. Yes, sir.
okay,
Yes, sir.
very
We can
good.
see that.
Very good. So that was the motion. You can see here the particle comes with some velocity. Maybe you will not appreciate it. It's a lot of buffering there. Otherwise, you could see that the particle comes with a velocity, and when it comes closer to the pier, it increases tremendously. The velocity increases tremendously, and it moves with much faster velocity, right? And that was this was basically our studies all about. So what we did was around this pier, we tried to understand how we tried to quantify the turbulence that was generated because of this external object in between the flow, right? So, and that turbulence was we try to relate it with this sediment motion, like what we did previously. But when you come to this study, two-dimensional will no longer work, and you'll see that when you talk about when you go through the flow, you'll understand what we did. Okay, so this was the one we had, and just to the diagram is like I have the flow, and in between I had a pier, and in the upstream side of the pier, all the flow that is changing there that was measured. You could see a grid line there, right? And that was the grid line which we have put there, and we have identified. Through the previous equations that till what level you will have till what length or what size you will have the turbulence effect around the pier that was measured, and 2 point times of more than that was selected as our study area location, and in that we try to measure all these turbulence characteristics using an ADV there. And you can see that there was an ADV there, and that ADV was used to measure the flow characteristics around the pier. And as usual, a camera was used to find out the sediment characteristics, and both we try to relate both of that, and we try to get a relation. That was the objective of the study. So you see, these many points we had. These were the points where the flow velocities were measured. You see, these many locations we had. All these points were the locations where we measured the flow. And you can see here, our measurement locations were very measurement points were very close, very dense, very close to the pier. It is very dense, and when you get away from the pier, we have increased the spacing between that, because we know that the changes, the effect of turbulence in the upstream side that reduces when it goes away from the when we go away from the pier. So that is the reason, and these many points we have measured, and each and every point you should understand as the 30 heads were used and 7,200 data points we got. Each and every point we got 7,200 data points, and the complete data points were processed to understand a map like this. And we got a very interesting map here, and you could see that how the flow velocity changes. Because of these many points, it was pretty easier for us to quantify where exactly the flow changes happens here. And you can see here the components of the velocity in x direction and y direction, and this u and v velocities were clearly captured using this. This all from the ADV data what we got, and that was processed. All that data was processed, and that was used for preparing this contour map. And this was the velocity changes, and you can see there very close to the pier, these diagrams were not possible. The data is not given, it is blank. Why? Because that was the limitation of the ADV. We could not go closer to the pier more than that. That was the maximum possibility with the ADV what we had. We had a lot of tilted orientations and all, and we could find this one, and that was a pretty decent data which we could get near the pier. And you can see that the velocity vector, how it comes and how it is getting diverted, and that is a very crucial area here, very close to the pier. It is very crucial, and that we try to understand, but unfortunately very closer to that we couldn't get that, but it was okay. And with that, as we did previously, we just measured the velocity values, and from the velocity values, instantaneous velocity values, these all turbulent intensities were found out. And you can see how the turbulent intensities varies close to the pier. And really, you don't have to bother about more than the size of the diameter of the pier. And that's what our previous literature also says, right? And the upstream side of the pier, you can see that it is not more than the diameter of the pier. It's less than that. All these effects will be felt within that. So whenever we have a study, we can have it just one time or 1.5 times if you want most, because all these variations will happen within that. And the flow along the separation line is the separation line. What I say is it is the mid this point here. What we have here, this is the line, and that is at that line where you have the flow gets diverted. So here, in the center line of that, the flow comes and hits here. That I call it as a symmetry line. And after that, the flow gets diverted in one's right side and left side, right? And this we have drawn that, and the flow variation we can see here how beautifully it is very varying. And you can see here the turbulent intensities are very high when it is closer to the pier as expected, or as on the lines. There's nothing particular about it, but it was really quantified what was the maximum turbulence level in very closer to the pier, and why it drastically drops down, right? And when it is very close to that, and you can see that it drops down, and that was really quantified. And with these values, we can draw the Reynolds stresses also, as computed previously. The Reynolds stresses and all these variation you can see here pretty close to the pier only. We have all these turbulence effects there, and other and upstream you don't have much effects there. So these all turbulence, the point to be emphasized here is these all turbulence really has an effect on the bed load. When these turbulence are not accounted into our predictions or whatever formulas we use, then it may not give you the correct answer. So that's what is the quantification from this diagram, and you can see the variation of the bed shear stress and the variation of the bed shear stress. Two formulas which we very commonly used in the literature. So that was also used to find out what will be the bed shear stress based on the values, and that was also these are all post-processed values, right? With this UV value, where these all things are post-processed, and we got a graph. So again, as usual in the straight flow, we got the diffusion factor. These are all same previous ways, flatness factor, kurtosis, and also we had quadrant analysis. Interesting diagrams we got. You see, very closer to the pier. It's all about the U dash, V dash, and W dash, right? So that were used to do the quadrant analysis, and based on that, we saw that there's a lot of things that is happening there closer to the pier. So it was a really, we could quantify this all turbulence that is happening there reasonably to some good extent. Um, and after, what happened? Hold on for a minute. Big images are coming up, so give me a minute. Hope you could see me.
Yes,
Can
sir.
you?
Slide.
Okay.
Yes, sir. We can see the slide.
Yes,
Thank you.
sir, we can see
Yes,
the
yes,
slide.
sir.
Thank you. So this was
Right.
like this was the worsening analysis of quadrant analysis. Through the quadrant analysis we have got, and the flatness factors, the kurtosis of that. So these all parameters were computed very close, because these all try to define the turbulence with all using the help of these all parameters. The turbulence we were trying to address, understand, and this all was again computed along the line, A line. A line is just the point of the symmetry line where it comes exactly in the upstream side of the pier, and B line is across that, it is in the 90-degree, and there are variation of all these parameters along this line, because that was our point where we are all focusing on. When it gets away from the line, it dilutes down. So that point we are having much focus on. So we try to quantify that along that line. And all these parameters which I have shown you in the contour map, by doing the post-processing of this contour map, we can get what are the velocities and other parameters at any point of interest. If you drop some points there, we can get the points from that contour map, and we can understand what are the flow parameters. Why I'm telling this is, each and every point very close to the upstream side of the pier was mapped. So at any point, what is the turbulence event, and what is the turbulent intensity, what is the kinetic viscosity, what is the turbulent kinetic energy, all this can be directly found out from these contour maps. So that was clearly quantified. Whatever we had in the upstream side of the pier, that was clearly quantified. And with that quantification, you see what the data which we got, that it is very pretty clear about the flow that is happening there. Now we go to the camera part. That is the image processing part. So here, this is an interesting setup which we had for this image capturing. So previously, if you see, we were using like it was a two-dimensional, two-dimension only. I mean to say that we had camera only in the side. So I had a flume there, and we had kept a camera in the side. So that camera was capturing all these sediment motion from only one side. But now you clearly understand that in the pier, it is no longer a two-dimensional. There is one more three-dimensional also happens there. So we cannot capture with one single camera. So what we did was we used two cameras. So one was capturing from the side, and the other was capturing from the top. So can you see that there is a camera in the top? Can you see? Yes,
Yes,
sir.
sir. Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir. We can see that.
Okay. So in the side, you have a camera, and in the top, we placed another camera. And what view we have in the top camera is also shown in the box. So in the what we see in the side is also shown in another box. And the two cameras were placed here. And the purpose of the camera, I'll tell you. What we are using from the side, that was a high speed camera. So only the data from that was used to measure the velocity of the particle. It was taking it from the side. So whatever we are capturing from the top, it was a regular camera. It was not a high speed camera. It takes some close to 34 frames per second. That is a regular camera. So that regular camera, it captures the sediment motion from the top. How a sediment moves, only that path can be tracked. It was a manual tracking, so we did not have a high-speed camera on the top. So these two were the camera setups we had, and with that camera setup, we tried to track a particle. You see, what we did here was, we know the complete flow profile. Okay, we know the complete flow profile, and I dropped a sediment in the upstream side. well ahead, we have dropped a sediment which was close to the symmetry line. But anyway, it was not passing through the way which I really wanted, but it was going, right? So I dropped a particle in the upstream side, so it was passing there. And the path of this particle was tracked using the data from the camera which I had from the top. So which I had from the top, that clearly captured the track of the path of the particle. So after what we did was, this track was superimposed over the contour maps what we have drawn already, right? And we have drawn already the contour map of all the turbulent characteristics what we have. Then what we did, we got the data along this track. What was the what were the turbulent characteristics properties, right? All that values we got it. Now we have a data, the velocity with what the sediment is moving, and what exactly was the flow parameters along this path. Along the path exactly, what was the flow parameters. Then we try to relate that both, so that we try to understand when the turbulence increases, how the velocity changes, right? So this relation was clearly found out by this method. So we'll see how we did this. This image was taken from the top. Let us see whether it works. It's working for me. Can you see that?
Yes, sir. Yes, sir.
Yes, sir. Yes.
Yes, sir.
Thank you, thank you. And you see this,
Yes, sir.
these all particles are moving. Can you see that colored particles are moving?
Yes, sir. Red, yellow.
Yes, sir. Little,
Yes.
little bit. We can.
How many colors you see?
Yes, yes, sir.
Okay. And I have used varieties of colors, and it was like a blue color, red color, yellow color. There is no specific hydraulic purpose behind that, and I have used 3 4 colors there. Why I use this, when I drop a group of particles in the upstream side, I really want to know which particle I am tracking, because it's manual identification and tracking. So I was putting 4 or 5 colored particles there. So in the upstream side, once I'll track yellow image, then yellow sediment, then I'll go through that. So that was the idea of having the color. Otherwise, no particular reason for having other color and the color code there. And you see, this is the interesting paths which we traced by using the camera in the top. We dropped a number of particles there in the upstream side, and all these particles were going in the path. You can see that it is getting skewed because of this turbulence, what is happening near the pier. It comes straight, and when it comes closer to the pier, these all particles get skewed. And these all paths were traced for all different particles. Which was closer to the symmetry line is grid 1, and which is very, very much away from the symmetry line is grid 6. Right, all these were traced from the top, and particles of different sizes were used, because we have seen that particle, when I used 7.15, it was rolling, and so 6 point something also it was rolling, and when it was 4 point and 1.7, it was saltating. So previously it was saltating, how it was behaving in turbulence, and previously when it was rolling, how it behaves in the turbulence. So that all we can really quantify. That is the reason why we have fixed the same sizes here. And this was some other images. I'm very sure you could not see there, because the buffering, it's very, very small particles, 1.7 particles there. And then that was also tracked, like all these only sample tracks were are shown here for the presentation purpose. If you ask me the numbers, it was running close to hundreds of tracks. It was close to 700 plus tracks were traced for each and every particle, so that we can really understand whether any effects are there. Maybe dropping issues, all that can be averaged out. That is the reason we did a number of tracks there. With all that track data, we could really quantify all that paths traced by the particles there. This was another 7.15 mm particle. And you see 7.15 mm is pretty heavier. And you can see that the skewness is not much of is there. Skewness is there, but you can see when you compare with this, there is a lot of changes pretty close to the peer. But here it is all there, but not that. So that also was traced, was found out, and 4-point particle. Then those all tracks were like from the camera that is captured from the top. We know how the particles are moving very close to the peer, right? Now what we did was we had a camera from the side, so that was also capturing. We could see that. Just make a try. Can you see?
Yes,
Yes,
sir.
sir.
Yes.
Yes, very good. So these are the particles that were moving from the side. So that was completely captured using the cameras from the side. So this data, what you got from the side, that was used for computing the velocity data about the sediments. So the top data was used to compute the, identify the tracks it was following, and from the side we have used the camera to find out the velocity of the tracks that it was tracing. And it was also again done for different sizes of sediments, sizes and shapes of the sediments. And as usual, 1.7, 6.5, 4.5, all were done. And this particle tracing was also done. You see how the particle moves, it's saltation, and you can see beautiful saltations. Previously, it was in rolling regime or close to rolling regime. When it comes closer to the pier, it starts saltating. So, do you see that? Previously, it was rolling very
Yes,
close
Yes,
to
sir.
the
yes,
pier.
sir. Yes, sir.
Yes. So it is all saltation that is happening just because of this extra turbulence that is created. In an ordinary, regular thing, it should not saltate, it should roll, but because of this extra turbulence, it's saltating. So we try to quantify that also. And this was the procedure that was adopted in particle tracking. So we had from the top video, we had 35 frames per second, and that was used to get that track. And each and every track, we got it from the side. We found out the velocity with what the particle was moving. So you can see here the angle of deviation, how much it is changing. All that could be easily computed by the image processing techniques. So we use many techniques there, and using that we can find out how much it is getting deviated. Because when the velocity vector also, when it changes, we can do the computation based on the angle, how much that corrections also applied. Why? Because you see, when you see the track the object from the side, there are some miss of data, because when you are taking it two-dimensional and there is an angle, if it is a straight line, there will not be an issue. When it is turning in an angle, that angle has to be resolved. So the resolution of velocity vectors were done so that the errors were minimized. And you could see that these were the variation of the beautiful graphs which we got, the beautiful values which we got. You can see that along the track from the contour maps, we try to extract these all data from that contour maps, and the velocity data we got it from the camera, and both we try to relate, and then we try to understand what was the relationship between that both. So here you can see that previously we had a equation, right? And with that equation, if you predict. That was also in a transitionally rough bed, and say the particles were moving with the same particles were used and the flow parameters were same. So if I use the previous equation without considering turbulence, you will say that the velocity is in the black line, bottom line. Can you see that? In the top graph, there are two lines. One is blue line and one is a black line. Can you see that?
Yes, sir.
Yes, sir.
Average value, and that will be the prediction which you make, and that will be an under prediction, very clearly an under prediction. So that what with this data, what we have done is, with this we have added a correction coefficient. When you talk about turbulence, what is the turbulence level in that area? Turbulent kinetic energy, what is the level in that area? Take that value. That can be found out very easily by any ADB or something. Find out that extra turbulence, find a correction coefficient, and this is added into that previous equation, so that we will have a correction. So after rewriting an equation with this correction coefficient, we got another equation, and when we predict this velocity with this corrected equation, we got that blue line. And you can see that it it makes a very good prediction. And this red line is the average velocity of with what the sediment was moving. So the velocity which was moving was in a red line, and then we had a prediction, that predicted equation that was also plotted, that is a blue line, and it gives a fairly good prediction. So this equation is really helpful when you are working on a transitionally rough bed. When you have a transitionally rough bed and the flow is happening and the bed is rigid, then we can directly use this equation, so that it will not make any under prediction. It will give you a fairly good prediction of the values which we get. So this was some other sizes. All these sizes were taken into account, and many of these diagrams were, it was meticulously analyzed. You see, all this, it's not a single track answer. We did the same thing for multiple tracks, close to 1,000. And if you ask me the data points, it was crossing crores, because at each and every point it was 7,200 data, that multiplied by 350 points, and that much of value. And if you track high speed images, each and every image you will have some 3,000 to 4,000 photographs that has to be evaluated, that into. So it was like full data. The data processing was really meticulously, it was done, so that we get these values. So based on all these track values and what we got, we concluded this equation. And these are some more tracks, the variation of the flow characteristics across the, on a typical track traced by a particle, and that was also compared. So based on that, we make the following conclusions. So it was a very detailed study was done, and this based on this study, then we can really find out that when the bed is transitionally rough, then definitely we can use this equation without extra turbulence. If you don't have any extra turbulence, use the first equation and you compute what will be the value there. And if you have any extra turbulence, use the second equation with the proper correction factor. That will be based on the turbulence level in that area. So based on that, we can make a computation there. And these were some of the conclusions which we could get from this. It's all very detailed conclusions, how much it is changing, why it is changing, at which point these changes happens, and at which level, which was the point till which the turbulence happens. So where this quadrant analysis point, where it was greater, And you see, at when we try to quantify this higher order moments and coherent structures using quadrant analysis around the peer, we saw that high values of these values are greater than 3 when the flow separation region. In the flow separation region, we could find that it was very high, and that really indicates that the turbulence is highly intermittent in that region. So that really tells us more about the turbulence. So we could really see, but a lot more work has to be done to understand the exact turbulence that is happening and how it is linking with this particle motion. And these were the conclusions which you could make. And I should really tell that this all work is the brainchild of my supervisor, Dr. U.C. Kotiari, and he was a great legendary man in this field of sediment transport. And it was his idea about trying to understand the influence of turbulence, because he was very much particular from the beginning that he clearly knew that there was from the beginning he was saying these all bed load transport equations that should include turbulence also. So we should quantify turbulence. So this was one such attempt that was made to understand the turbulence and the influence, and we could quantify to some extent. And a lot more work should have been done in this field of sediment transport and turbulence, so that we can understand things better. And that's what I have in my presentation today. Dr. Sudhanshu, Dr. Jain.
Yes, sir. So, dear participants, if you have any questions, then you can ask. Any doubt?
Sir, I have one question. Can I ask?
Yes,
Yes.
please go ahead.
Sir, during the presentation, you said due to the limitation of ADV,
Hmm.
we can't identify the contours near the pier.
Ah.
So, is there any instrument in present that can eliminate this limitation?
Non-contact velocity measuring devices, maybe laser. PIV could be used, but this our flow was very huge, and I don't know whether PIV was used for very small applications, small things. But non-contact measurements, whatever you have, I guess that can be used to find that.
Okay, sir. Thank you.
Any other points which?
Any other question?